All right. As promised before the break, I said there are two ways we can view this equation, unfortunately, because there's a sign difference involved, which can be quite a headache. So let me show you. So one way to consider this is the so-called passive view. So in the passive view, A is an operator which rotates the entire coordinate system. So it rotates the coordinate system from the unprimed to the primed one, but it leaves the vector r intact. So in this way, this equation gives us the components of r prime. Or it gives us the components of R in the prime system. So R is left at rest, and we only rotate the coordinate system. So that what we get here are the components of R in the prime system. That's one way of doing it. So then A rotates the coordinate system counterclockwise. In the active view, A is now an operator that rotates the vector r clockwise instead of counterclockwise to a new vector r prime while leaving the coordinate system unchanged. So the difference between the active and the passive view is that in the passive view, you actually go to a new coordinate system. You're only dealing with one vector, which you then express either in the unprimed or the primed system. In the active view, the matrix A rotates the vector itself, and you're only dealing with one coordinate system. Now, in order to use the same transformation matrix, which is written here, you have to rotate the coordinate system counterclockwise in this case, and clockwise in this case. And we can see this from the figures. You see that we have to rotate the coordinate system, the prime coordinate system, in this way for r to get closer to the x-axis. Whereas here, you would have to rotate r clockwise to get r prime closer to the x-axis. And this clockwise, counterclockwise business basically amounts to dealing with either phi or minus phi. So cosine is invariant if you use phi or minus phi, but sine isn't. So rotation in one direction, given like this, well, then we have rotation in the opposite direction, given by doing this. So that's something you actually have to be a little bit careful about. You have to keep in mind what this equation actually represents for your particular system that you're analyzing, your problem. And also remember this, that you have different directions in the two cases, corresponding to minus or plus on the signs. So I'm sure there's a great way of remembering this, making some system to memorize it, but unfortunately I can't give you one now. I can only advise you to be aware of this. Okay, having now derived this transformation matrix, we're going to have a look at some of its mathematical formal properties, which will be of great use for you as you later will proceed to analyze different types of rotation. So we'll basically introduce a couple of mathematical tools for you to put in your arsenal, which then will be handy when dealing with various problems. So consider first the scenario where we have two successive transformations. So we start out with a vector r and then transform it, according to this equation, to some new vector r prime. And then we transform this vector again to some r double prime. So we can associate a transformation matrix, which we may call B, with this transformation here. And then we associate some transformation matrix A with this transformation here. We then have the following equations, which are just the matrix, which is just the matrix equation here, written out in component form. So x prime is obtained by letting B operate on the unprimed vector, and x double prime is obtained by letting A operate on the primed vector. If I now take this expression for xk prime and insert it here, I get an equation which directly relates x double prime to the unprimed quantity, like so. And keep in mind, this is a sum, because we have two repeated indices. So I define this as Cij. And what this means is that two orthogonal transformations, successive, one after the other, is equivalent to a third one, described by these elements. So two orthogonal transformations in succession are equivalent to a third one, given like this. Now, I've written that C is also an orthogonal transformation. What would you say is the condition for C to be an orthogonal transformation, expressed through its element Cij? So I'm saying that C is a matrix which corresponds to an orthogonal transformation. So if you want to check this, what kind of condition do we need to have on the smallCij's, the elements of large C? Any ideas?
The same one as we had for A?
Yep. Exactly. So we need, let's see here. And I'm not going to show it here, but you can show that if A and B are orthogonal transformations, meaning that their elements satisfy this type of equation, then C, the elements of C, will also satisfy this equation. And you can inspect this by just inserting the definition of C here. So that's one thing which is very handy, that two successive transformations is equal to one, is the same as one effective orthogonal transformation. Also, it's important to be aware of the fact that A and B do not commute in general. So what this means is that the order of transformation, the order in which you rotate something, matters. You can't just exchange the orders and get the same result. And we'll have a look at a specific example of that in a little while. So these orthogonal transformation matrices are non-commutative, but they are associative, meaning that they satisfy this property. So keep in mind that the order of rotation actually is important. Having defined now the transformation A, let's say a few words about its inverse transformation. Which we denote like this. And we write the matrix elements as Aij raised to the power of -1. But keep in mind that this is not equal to 1 over Aij. This is just notation. This is just a way of writing the matrix element of this matrix. So A inverse, the inverse matrix transformation, we know in advance that it should physically take us back to the original state. If A transforms the vector r to some new vector, then the inverse transformation should take us back to the original vector. So in terms of this inverse transformation matrix, xi should be equal to this. Well, this means that if you combine this equation with the original transformation from the unprimed to the primed system, which looks like this, it has exactly the same form. So now I insert this here. I obtain the following relation between the transformation matrix elements A, Ki, and the inverse transformation matrix elements Aij -1. Because what I should end up with is the same thing. I should have xk prime is equal to xk prime over here. If we now inspect this sum, because it's a sum, we have repeated indices I here. You see that this is just a way to write out element-wise the product between these two matrices. Whereas this is just the matrix elements of the identity matrix. The identity matrix has non-zero entries only along the diagonal, which can be written like this Kronecker delta. So we have this relation, the transformation matrix A multiplied with the inverse transformation has to be equal to the identity matrix. And this makes sense because we just stated here that the inverse transformation has to take us back to the original state. So it's like acting on our original state with the identity matrix. Nothing happens. And let me just comment here that A and A inverse actually commute. So we just stated over there that two transformations, A and B, do not commute in general. However, in this specific case, they do commute. So whether you rotate R by an angle phi and then back, or if you rotate it an angle minus phi and then back, it's the same thing. So A and its inverse do commute. Let's see now if we can make use of some of these properties which enter an orthogonal transformation, namely these orthogonality conditions. Let's see if we can make use of that to find some simplified way of obtaining this A inverse. Well, we always have some way of obtaining A inverse. We can just use the matrix rules that apply for finding the inverse of a matrix, but you know that these can be quite hairy, especially if the matrix becomes large. But perhaps there is some simpler way in this particular case of orthogonal matrices. So with this as the motivation, consider now this double sum. It's a double sum because we have repeated indices k and also repeated indices I. So this should be equal to something that depends on the indices j and l. We know that if A is an orthogonal matrix, it has to satisfy these orthogonality conditions, 3 of them. So if I now insert this here, I have delta IL multiplied with AIJ inverse. And in fact, this double sum becomes ALJ inverse. So that's one way. That's one relation. We have that this is equal to this. Now let me use a different orthogonality condition. Or in fact, let me use this equation here, which relates A and A inverse, stating that their product should be equal to the identity matrix. So if I now use this equation here, and we do so to obtain AJL. Because we'll only have contribution from when K equals J of this term, so it's AJL. And now we're in a pretty good position because we have one expression here for the double sum, and we have another one here. So we have this relation here. Oops. Now AJL is equal to ALJ of the transpose matrix. The transpose matrix, or the transpose operation, essentially means that you interchange columns with rows. So you interchange these two indices. So then we have this relation. So we see that the ljth element of the inverse matrix operation A is equal to the ljth element of the transpose matrix of A. And since this relation holds for each element, we can actually conclude that the inverse matrix operation A inverse is identically equal to the transpose matrix A. So for orthogonal matrices, the product between A and A transpose is equal to 1, since A transpose is the matrix inverse. And this is really good news, because it basically tells us that to obtain the inverse matrix A, we just have to change the rows and columns, instead of actually calculating the inverse of the matrix. And this simplifies things a lot. Okay, so far what we have is that A and A inverse commute, and the product is equal to 1. And if A is an orthogonal matrix, we know that its inverse is equal to its transpose. Let's see if we can find out even more. Consider now the determinant of the matrix. A general property of determinants is that the determinant of a product of matrices is equal to the product of the determinant of the matrices, like this. We know that the product of A and its transpose is equal to 1. So by using this general property on this expression, we obtain this, since the determinant of the identity matrix is equal to 1. We know one more thing about determinants, and that is that they do not change if you interchange rows with columns. So that means that the determinant of the transpose of a matrix should be equal to the determinant of the original matrix. And that thus leaves us with only two possible choices for the determinant of an orthogonal matrix. It's either plus or minus 1. These are the basic mathematical tools which will be helpful for you as you analyze various classical mechanical problems involving in particular rotation. And by the way, you can convince yourself that the rotation matrix we introduced for 2D satisfies that property. So with these tools in our arsenal, we should now try to take one step further and say something about which coordinates are then suitable as our generalized coordinates to describe a problem in this context. We saw that the directional cosines didn't quite do the trick because we had 9 of them, but only 3 were independent. Enter the Euler angles, which is a common choice for generalized coordinates in this context. But we saw that when taking into account the 6 normalization or orthogonality conditions in 3 dimensions, we should be guaranteed to be able to find 3 functions of these directional cosines which are independent. However, if we're interested in physically possible rotations, we actually have to introduce one more condition. So to see this, consider this coordinate system. And let me now perform a transformation on this coordinate system, which takes it to a new coordinate system. So as you can see, what I've done here is that I've just inverted all the axes. I've taken y and let it go to minus y, taken z, let it go to minus z, and x to minus x. Like this. So if we have that this is the general transformation equation, and in our particular case, A is equal to this S transformation, which inverts all the axes. What will A be? Or S, what will S be? Well, we can start by asking, does it have any non-diagonal entries? No, because there's x prime is only related to x, y prime is only related to y, etc. If x prime was expressed as a linear combination of x and y and z possibly, then we would have non-diagonal entries. So we only have potentially diagonal entries. I saw you raising your hand, so do you have a suggestion?
The S has to be minus the identity matrix.
Right. So by multiplying this with, x, we obtain these equations. So what I would like you to do now for the next 30 seconds is to see if you can find some way to rotate this system to obtain this. All right?
You can't, because you've changed from a right-hand system to a left-hand system.
Exactly.
And rotation doesn't do that.
Does anyone have any way that you can rotate this to this? Any counter proposal? No. I would be very surprised if you did. Because exactly as you say, we're turning a right-hand system into a left-hand system here. So there's no way you can take this and rotate it into this. So if by physically possible rotations, we then mean something which this is not a part of physically possible rotations. This is outside the set of physically possible rotations. And we see that the determinant of the transformation matrix which performs this inversion, this is in fact an inversion. We see that the determinant is equal to -1. So that's our extra condition. We have 3 independent generalized coordinates, but they must be such that the determinant of the transformation matrix is equal to +1, because we've seen here that -1, which is a possibility for orthogonal matrices, but -1 corresponds to an inversion of the system axis, which is impossible to obtain from a physical rotation. So as stated in the introduction of this lecture, to completely specify the location and orientation of a rigid body, we need 6 degrees of freedom. 3 of them go to specifying the, for instance, center of mass of the rigid body, and the remaining 3 go to specifying the direction. So we need 3 independent parameters, or generalized coordinates, to specify the orientation of a rigid body. And these coordinates must be such that the determinant of the corresponding transformation matrix is equal to +1 and not to -1. And as we will see in the next lecture, the most common choice for this are the Euler angles. And we'll have a detailed look at them next time. Okay, see you later.